we will learn about the voltage control oscillator. So as its name suggests, it is an oscillator whose frequency can be controlled by the external voltage. Now in the conventional oscillator, the frequency of the oscillation can be selected by the passive components like the resistive capacitor and the inductor. And by changing the values of these passive components, it is possible to change the oscillation frequency. So in the conventional oscillator, if we want to change the frequency, then we need either a variable resistor or the variable capacitor, and manually we need to tune these components to change the frequency. So this voltage control oscillator also needs these passive components for the frequency generation, but with the given set of passive components, just by changing the control voltage or the tuning voltage, it is possible to change the oscillation frequency. So we can say that the voltage control oscillators are much easier to tune compared to the conventional oscillators. And in fact, if we want to tune the VCO using the microcontroller, then also it is possible. For example, if the digital to analog converter is interfaced with the microcontroller, then using the microcontroller, the output of the DAC can be changed, and by applying that voltage to the VCO, it is possible to change the frequency. So these voltage control oscillators can change or tune the frequency in a particular range, but commercially available VCOs can work from few hertz to even tens of gigahertz. And because of that, they are widely used in the communication applications. So they are used in the modulation and the demodulation circuits, as well as in the frequency synthesizers and the function generators. And these VCOs are integral part of the phase lock loop.
Oftentimes in ham radio you'll want to make a tuned circuit using an inductor and a capacitor in parallel, but you may not have convenient means of using a variable capacitor in the conventional sense, the kind with the meshed plates and all of that. But you can create a tuned circuit in your ham radio, for example in a transmatch or a radio amplifier or oscillator, using a varactor diode along with a conventional diode and an inductor arranged in a fashion such as is shown here. This is a parallel tuned circuit, and the way you tune it is to vary the voltage across this varactor diode. Notice that this is reverse bias voltage. The greater the voltage, the less the capacitance, and the higher the frequency. You can therefore have what is known as a voltage controlled oscillator. When you have a circuit like this, you in effect have a tuned circuit whose frequency is adjusted by means of a voltage applied to these terminals right here. It's commonly done in VHF and UHF ham radio equipment, but also to some extent in HF ham radio equipment. It's easy enough to build a circuit like this yourself. You just need to use the formula for resonant frequency, remembering that the capacitor here, which keeps the coil from shorting out your control voltage, this capacitor here appears in series with this capacitor or varactor here, so you need to calculate the capacitance based on that series combination and then use the formula for parallel resonance. A voltage controlled oscillator or voltage controlled resonant circuit can be built easily enough this way.
In the tank circuit of the Colpite oscillator, if the capacitors are replaced by the varactor diodes, then it can be used as a VCO. That the varactor diode acts as a variable capacitor. That means as we change the applied reverse bias voltage across this diode, then the capacitance of this diode will change. And by changing this reverse bias voltage, we can change the oscillator frequency. Now for any type of RC or the LC oscillator, the frequency is proportional to 1 divided by square root of C. And for the varactor diode, as we increase the voltage, then the capacitance of the diode will reduce. That means as we increase the control voltage, then the frequency of oscillation will increase. So as shown in the figure, this F0 is the nominal frequency when the control voltage is equal to V0. So when we change the voltage from V minimum to V maximum, then the frequency of oscillation will change from F minimum to F maximum. And here, if the control voltage is also varying with the time, then mathematically the frequency of oscillation can be given by the following expression. So here F0 is the nominal frequency of oscillation, while this voltage Vc is the control voltage. And this K is known as the tuning gain or the tuning sensitivity of the VCO. So it defines by what amount the frequency of the oscillation will change when we change the control voltage by the 1 volt, and it is defined by the unit of Hertz divided by volt. So this is about the voltage controlled harmonic oscillators. So now let us talk about the relaxation oscillators. So in a relaxation oscillator, by changing the charging current of the capacitor, it is possible to tune the frequency. So in this type of oscillators, the charging current is proportional to the tuning voltage. That means by controlling this tuning voltage, we can change the rate at which this capacitor charges. Now using the Schmitt trigger, the voltage across the capacitor is compared with some reference voltage, and when this voltage across the capacitor reaches this reference voltage, then the output of the Schmitt trigger will change. And with the change in this Schmitt trigger output, the polarity of this reference voltage as well as the direction in which this capacitor charges will also change. So in this circuit, if we see the output of the Schmitt trigger, then it will be a square wave, while if we see the voltage across this capacitor, then it will be the triangular wave. So here the frequency of this waveform can be controlled by the tuning voltage. So many voltage control oscillator ICs work on this principle.
PLLs, or phase-locked loops, as they are often called, are used in many areas of RF design.
They are a key building block for designers. They can be used in many ways and for many things. For example, they can be used for FM demodulation, signal reconstitution, clock recovery, but possibly one of the largest uses is within frequency synthesizers. These synthesizers are very frequency stable, and they allow digital lines from circuits like microprocessors to control the frequency. The operation of a phase-locked loop is based around the concept of phase. To get an idea what this is all about, we can take a look at a standard sine wave and see the different positions on the waveform. A complete cycle can be viewed not only as a sine wave as seen on a scope, but also as a point rotating around a circle. If 2 points are seen on the sine waveform, these can be considered as having an angle between them by looking at the circle, and this can then be said to the phase difference between them. This can be measured in degrees, where there are 360 for the complete cycle, or it can be measured in radians, where there are 2 pi radians for the whole cycle. The idea of phase is important to grasp. Rather than taking the phase difference for 2 points on one waveform, phase difference can also be measured between 2 waveforms by taking the same point on each of the waveforms and seeing the angle between them. This phase difference may change with time, or it may remain the same. If it doesn't change, it means that the 2 signals are moving around the phase circle at exactly the same rate. If they're moving around the phase circle at the same rate, they must be oscillating at exactly the same frequency. The key here is that if the phase difference is not changing, the frequencies are exactly the same. This concept is put to use in a phase-locked loop. Let's look at the building blocks first. There are 3 main elements in the loop. There's the phase detector, voltage-controlled oscillator, and the loop filter. And I suppose one could say that the reference generator outside the loop is also important, but it's not part of the loop itself. So let's look at these elements in turn. The first one's the phase detector. In many ways, this is the key element of the loop. It takes in signals from the reference and the voltage-controlled oscillator and produces a voltage proportional to the phase difference between these 2 signals. The next block is the voltage-controlled oscillator, or VCO. The VCO can have a number of voltage to frequency curves. It may be linear, or it may have a slight curve to it. The main thing is that it must be what is termed monotonic. In other words, it must always go up in frequency for an increasing voltage. Finally, there is the loop filter. This is a really key element of the design because it governs so many of the loop characteristics. It's surprising in many ways because this circuit is often no more than one or two resistors and a capacitor. Anyway, this filter does a number of things. It attenuates the level of the reference frequency appearing at the output. Its aim is to provide a near DC control voltage to the control input of the VCO. However, it also determines much of the phase noise characteristics of the output signal. It controls the frequency agility, whether it can quickly change from one frequency to another, and finally it governs the loop stability. So if we look at the phase-locked loop as a whole, we see that these three main blocks are interconnected. The phase detector takes inputs from both the reference and the voltage-controlled oscillator, and it produces an output proportional to the difference between them. This different voltage then passes through the loop filter to reduce the high-frequency components, and then it's applied to the VCO to control its frequency. The error voltage from the phase detector is in such a sense that it tries to reduce the phase difference between the VCO and reference signals. It draws the VCO frequency towards that of the reference until there's a steady state phase difference. As there is a fixed phase difference between the two signals, it means that the frequency of the reference and the VCO are exactly the same. The loop is locked. So what's the use of producing a signal on exactly the same frequency as one you already have? If you look at it simply like that, none at all. But if you use the phase-locked loop in a more imaginative way, it can be used for many useful applications, from FM demodulators to synthesizers and much, much more.
Phase-lock loop or electronic phase-lock loop initially came into existence in early 1930s itself for obtaining synchronization in radar systems and also in other communication systems. Let us look into the block diagram of the PLL and its fundamental working principles. Here, the input signal here is a signal which has a frequency Fs and a voltage of Vs. This is a signal which has to be get tracked, right? So here this signal is given as input to a phase detector. The other input to the phase detector is the output of a voltage controlled oscillator. Why the name given here is a voltage controlled oscillator is this VCO has a free running frequency of F0. The free running frequency is nothing but the initial frequency to which the VCO has been set, right? So why it is called as voltage controlled oscillator is depending upon the applied control voltage VC, it is possible to shift the frequency of the frequency oscillator either in the positive or in the negative direction. That is why this VCO is called as voltage control oscillator. So now returning back to this part, the phase detector accepts the input signal with the frequency Fs, and initially the signal from the output of VCO which is said to be F0. The phase detector is fundamentally a multiplier whose output is going to be nothing but addition of the frequency component and subtraction of the frequency component. So the output of the phase detector will be Fs plus F0 and Fs minus F0. That is, the output of the phase detector will be an error voltage VE which will have a high frequency component as well as low frequency component. So now let us initially assume that there is a vast difference between this signal Fs and the free running frequency F0. So when there is going to be a vast difference, this Fs plus F0 will be very high, and Fs minus F0 will also produce a difference component which will have a finite amount of value. So this error voltage is passed through a low pass filter. So the output of the low pass filter will be nothing but the low frequency component alone, because the high frequency component gets filtered. So initially when Fs is going to be very far away from F0, we will be having a considerable amount of voltage, DC voltage over here. So this DC voltage is amplified by the error amplifier and applied as a control voltage to VC0. So when this control voltage is going to be a significant value, it will try to shift the frequency of F0. So what happens is the F0 value now will get shifted to a new value, say F1. So again this F1 and Fs are compared, and then it produces Fs plus F1 and Fs minus F1. So now this difference Fs minus F1 will be comparatively lower when compared to the previous case. In this manner, again the voltage Vc will be obtained. In the same manner, it will again shift the new frequency F1 to some other frequency. So this process goes on repeating till the output of the VCO gets equal to the input frequency Fs. So once the output of the VCO becomes equal to the input frequency Fs, the PLL is said to be in locked condition. So once the PLL is said to be in locked condition, whatever changes might be there in the input signal, the PLL will be able to track the changes in the input signal. However, it is possible that if the input signal varies or changes away to a large extent, the PLL can go out of the lock. So this is the fundamental working of the PLL. So as I told you here, when the value of this error voltage is said to be maximum, definitely your PLL will be not be in locked condition. You can see that the error voltage is going on changing. Sometime it is high and sometime it is getting low, and again it is getting high and again it is getting low. So finally at one particular case you can see that the error voltage becomes equal to 0. So only when the error voltage becomes equal to 0, the PLL is said to be in locked condition. When the error voltage is said to be in 0, the VCO output is not allowed to change. So it means that PLL has entered into the lock condition. So the process of capture, the loop achieves a condition of being in lock with the signal from a free running and unlocked condition. This is called as a process of capture. So what is FC? The VCO operates at FC, or sometimes it can also be told as F0, which is called as a free running or the center frequency. Then what is called as capture range of PLL? The range of input frequencies around the center frequency, that is, assume that the VCO frequency is going to be F0, and what are all the range of frequencies around the F0 where there is a possibility that input signal can get tracked. That from an unlock condition it will get into lock condition. That is called as capture range of PLL. Pull-in time. Pull-in time is nothing but the total time required for the loop to get captured with the input signal. Told a phase detector is fundamentally a multiplier. So there are two types of phase detector: analog phase detector and digital phase detector. So now we'll see about analog phase detector using electronic switch. So here we have seen that it is an input signal Vi, and then output from the VCO, which is again given to the phase detector. So we are assuming here now that the input signal Vi and the drive from the VO are with the same frequencies, right? So even if they are at the same frequencies, there will be, or you can expect, a phase difference between these two signals. So this phase is a very important thing. Depending upon how much phase difference is there between these two signals alone determines what will be the output error voltage. So the analysis of phase becomes very important over here. So let us assume here that this square wave output is going to be your VCO output. VCO output will always be a square wave. So this is a VCO output with a particular frequency, and I'm assuming that my input signal is also going to be some signal which matches with the frequency of this VCO output. However, we are going to take three cases where the first case, the phase difference between both the signal is said to be 0. The second difference is the phase difference between both the signal is said to be 90 degree, and the third one, the phase difference between both the signal is 180 degree. So in the first case, if you see, if you try to calculate the average error voltage over here, it is very visible that if you take an average of all these, right, you will be definitely getting an error voltage which is said to be positive, right? Whereas when the phase difference is going to be equal to 90 degrees, and when you take the average error voltage, you can see that half will be contributed here, half will be contributed again here and here. You can see that the net voltages will cancel each other, and the resultant error voltage VE will be equal to 0, right? Similarly, if the phase difference is going to be equal to 180 degree, so if it is going to be in this manner, then if you try to calculate the value of the average error voltage, you will be getting a negative error voltage. So the conclusion here is, when the phase shift between the two signals is equal to 90 degree, we get the output error voltage as 0. Once you get the output error voltage as 0, it means that the VCO will not shift its frequency further, or when the VCO does not shift its frequency further, it means that the PLL has been set to acquire in the lock condition. So this is the operation of analog phase detector using electronic switch. So let us discuss about the most important part of your PLL, which is nothing but the voltage control oscillator, VCO. And the VCO is now realized using a single IC NESC566. It's very important even when you come into exam point of view. So you can see that it has 8 pins, where you can see that the modulation input is applied at pin number 5. And then this C1 and R1 is very determinantal in determining the output frequency of your VCO. And then you can see obviously VCC and ground. The next part that we are going to see here is low pass filter. So low pass filter is obviously the same one. It is going to be nothing but output of the phase detector is given as input to the low pass filter. A low pass filter has to filter high frequency and pass low frequency. This is just a single pole RC, and here again this is one more type of phase one more type of low pass filter, and then again this is the third type of low pass filter, which is these two are nothing but passive filters, whereas this one is said to be an active filter, which involves an op-amp in it. We have seen about the advantages of active low pass filter when compared to passive low pass in our earlier units itself. So this output of this low pass filter is only passed as an error voltage or the control voltage given to the VCO.
Look around you. Every piece of technology you encounter contains some kind of frequency generator. Now, if you're a computer engineer, you call this a clock. Not like a kitchen clock or a bedroom clock. It's not there to tell the time. Instead, it's more like a metronome, keeping a steady rhythm, like an orchestra conductor keeps all the musicians playing at exactly the right tempo. In a computer, everything has to be precisely timed so that data arrives where it's needed, exactly when it's needed. But if you're a radio engineer, you probably call the frequency generator an oscillator. A radio transmitter uses an oscillator to generate a pure sine wave called a carrier, precisely on the transmit frequency, and then uses a modulator to impress the information to be transmitted onto the carrier. In the receiver, a signal from a local oscillator can be mixed with the received signal to help recover the information that was impressed onto the carrier. These oscillators have to be precise to ensure that you're transmitting on the right channel and not interfering with other users. But having a fixed frequency generator just isn't enough. Most of the time, you need some kind of frequency generator that can change frequencies easily. Don't believe me? Well, think about two common applications. First, in your car you probably have a radio, and unless you're driving an antique, that radio has some buttons and a digital display for the frequency. Well, how does that work? The answer is that there's an agile frequency generator inside that forms the local oscillator that we just talked about. The frequency generator can be configured to produce a wide range of frequencies, each frequency corresponding to a channel on the AM or FM bands. If you had only a fixed frequency generator, you could only receive one station. Boring! The other application is probably right in your pocket, your mobile phone. Hey, have you ever stopped to consider just how many radios are in a common cell phone? There's at least one for the cellular function, another one for Wi-Fi, and yet another one for Bluetooth, and still another one for near-field communication. Hey, that's a lot of radio transceivers in there, and every one of those transceivers has to be frequency agile. Frequently, you'll see the performance specified at a 100 kilohertz offset. If you have a clock source with a noise margin of minus 130 dBc per hertz at a 100 kilohertz offset, then you have a good clock that's probably sourced from a crystal oscillator. Now that we have a stable oscillator, let's crack open that M over N divider. Now the first thing to recognize is that M and N are both integers. That is, at its core, we're multiplying the input frequency by one integer factor and dividing the frequency by another integer factor, and not necessarily in that order. Now, I'm not going to go into the details about how to build a generic divide by n counter, but if you're interested in following up, do a quick search for synchronous counter. There are lots of resources out there that merit your study. So that's how you divide an input frequency by any integer you like. You can take a 10 megahertz signal and create a 5 megahertz signal, a 3.33 megahertz signal, a 2.5 megahertz signal, a 2 megahertz signal, just by dividing by 2, 3, 4, or 5, or you can do any other integer division you want to consider. But what about frequency multiplication? Well, to understand that, we're going to have to take a little detour. And that detour leads us to the phase-locked loop. That's a bit of a mouthful, so engineers have shortened this to just PLL. The PLL is one of the fundamental building blocks of modern RF technology, and so we're going to spend a little time so we can really understand it. This is a basic phase-locked loop. Every PLL contains three main blocks: a phase detector, a low-pass analog filter, and a voltage-controlled oscillator. And that's it. I mean, it looks pretty simple, but there's actually a lot going on here. Now, to start, let's assume that the input frequency and the VCO frequency are the same, and that the two signals are in phase. Now, in that case, the phase detector sees two in-phase signals, so its output is 0. Feed a 0 value to a low-pass filter, and you'll get a 0 output. That 0 output is passed to the VCO input, so the VCO doesn't change its output frequency. The loop is stable, and in this condition the loop is said to be locked. You'll see why in just a moment. Okay, now let's say that the input frequency begins to drift higher. The phase detector will begin generating positive pulses toward the low-pass filter. The filter will smooth and average these pulses to a rippling positive DC level, forcing the VCO to run faster until the input frequency and the VCO are once again in phase at the same frequency. The system is still stable, and the loop can still be said to be locked. Now consider the case where the input frequency begins to fall. Now the phase detector begins generating negative pulses that are rectified by the loop filter to create a negative DC level. That forces the VCO to run more slowly until, once again, the input frequency and the VCO are in phase and matched in frequency. Now the system is still stable and the loop is still locked. And really the only way the loop becomes unlocked is if the input frequency varies too quickly or by too great an amount for the loop filter and the VCO to keep up. In such a case, the loop is said to be unlocked, but it will lock again when the input frequency returns to the lock range of the loop. Now, one common use for phase lock loops is for an FM demodulator. Now think about it this way. If you apply a frequency modulated signal to the input, the phase detector and loop filter will try to push the VCO to track the input signal, and as a result, the amplitude of the output of the loop filter will track the input frequency and present a pretty good representation of the modulation waveform. This technique is currently the most commonly used method to demodulate FM signals in modern receivers. Yeah, but we're not putting an FM signal into the phase-locked loop. We're putting in a pure, constant frequency. So what will we get at the VCO output? Well, we'll get a pure, constant frequency, so What's the point? Well, the point is in the feedback loop. What if we put one of our frequency dividers that we just learned about into the feedback loop? Now, we can start with something simple. Let's say a divide by 2 block. Now, if you add a divider block, the phase detector will sense that the loop is unlocked, and it will try to push up the VCO frequency so that the input frequency and the feedback frequency are the same. But to do that, it has to push the VCO frequency so it's running twice as fast as the input clock because of the divide by 2 in the feedback loop. And when it finally does get back into lock, the PLL will be generating a nice, clean, stable signal at twice the input frequency. Here's a little more detailed diagram of what goes on inside a phase lock loop. First, let's talk about the phase detector. Now, not all phase detectors generate 0 volts at 0 phase difference. Now, in this case, the phase detector produces a 50% duty cycle waveform when the divided VCO frequency and the crystal oscillator have the same frequency but are exactly 90 degrees out of phase. When the VCO runs faster than the crystal oscillator, the phase detector produces a duty cycle less than 50%, which slows down the VCO, which keeps the two signals exactly 90 degrees out of phase. And when the VCO runs more slowly than the crystal oscillator, the phase detector senses the change and produces a duty cycle greater than 50%, and that speeds up the VCO. And once again, the two signals stay exactly 90 degrees out of phase. Now, for a lot of PLL designs, this makes a lot more sense than a true bipolar design with 0 phase shift. The loop filter and the gain block smooth the pulse train to create an average DC level. At a 50% duty cycle, the average DC level should be exactly 1/2 the full range voltage, and a smaller or larger duty cycle causes the DC level presented to the VCO to rise and fall as well. Now, assuming the VCO has a wide enough range, increasing the frequency divider's divide ratio will make the VCO output frequency increase. Put in a 1 MHz crystal, set the divide ratio to 10, and you'll get a 10 MHz output.